Okay, so I'm going to make a quick tutorial on the review from Chapter 5. I'll first start out with electromagnetic radiation. So electromagnetic radiation is important to know for the test. So see here as we pull this up, it's pretty blurry, but it has everything we need. So first we're going to need to remember that radio waves have the longest wavelength, and it gets shorter as we move to the right. So microwave is the next longest, infrared is the next longest, visible next, ultraviolet, then X-ray, then gamma ray. Also, we need to remember how these are related, and that is by C equals lambda nu, where lambda is the wavelength, that doesn't make much sense doing that like that, and nu is the frequency. Okay. So if we're looking at this, let's look at question number 3 on the review. The question asks, the distance between the same 2 points on adjacent waves is equal to 1 what? So what this is asking about the wavelength. So wavelengths are measured by definition of peak to peak. But if you have 2 points on adjacent waves, adjacent means next to. So if that is the wavelength by definition, this would also be the wavelength, because they're on the same point and they're on adjacent waves. So from peak to peak is going to be the same distance as that. So that is the wavelength that you're looking for on number 3. We'll zoom out of this a little bit. Okay, and we will look now at how these are connected again. So this got really small now, so let's write it again over here. So C equals lambda nu. If we look at number 4, the relationships between these, we'll also want to think about E equals H nu. Okay, so if we rearrange this equation to put C on this side with lambda on this side, equaling nu here, by just dividing this over, then we'll end up with this equation. So if we look and see at the first question in question 4, A asks, as the wavelength increases, frequency does what? So we're looking at this, we say, okay, the wavelength is going to increase, so that's going to make this whole side smaller, so that must mean that frequency gets smaller and goes down. So as wavelength increases, frequency decreases. Okay, the next 2 problems are talking about this equation here. So we have to do a little more rearranging. It's going to ask us to say what's going to happen to the wavelength. As the wavelength decreases, the energy does what? So as the wavelength is associated to energy in this way. And how I did this is I just said, okay, so if this is nu and that is nu, then I can just plug this in. So I just plug this equation into that part there, and I get this equation now. Okay, so the question asks, as wavelength decreases, energy does what? Well, if this decreases, then this entire side gets bigger because we're dividing by a smaller number. So that means that goes up. So as the wavelength decreases, energy increases. And for the last question, we just have to look at this equation because it asks, as the frequency increases, what happens to the energy, and it also will increase. If you times this one by 2, this will go up by 2. Those are called directly proportional. So electrons and light. We did a packet on this, and I'll draw a small diagram. Maybe we'll go one more on there. Okay, so let's number those. So let's say this is the first 1, 2, 3, 4, 5, 6. Okay. Okay, electrons and light. So the question here says, when viewing an emission spectrum, the distinct bands of light that are emitted correspond to, well, what do they correspond to? So if we remember from the packet, it showed Bohr's model of the atom, how it has distinct energy levels. These are called quantum. They are like rungs on a ladder. The electrons have to be on these rungs, essentially. They cannot be anywhere else. As we know now, they don't look exactly like nice, perfect circles orbiting the nucleus. They kind of have some weird shapes sometimes, but they have to be in those areas, and they can't be anywhere else. As they go up in energy, as electrons go up in energy, so let's put an electron up here somewhere on the 6th, and as it comes down, let's say it comes down to the 2, it emits some sort of light. Okay. So emit some sort of light. So let's look at a different one. If we went from 4 to 2, it would also emit some light. But it wouldn't emit the same color of light. Like this one might be blue. So why does it do that? Well, if we think back again on what we just learned about frequency and wavelength and energy, we can see that the change in energy from here to here is different from the change of energy from here to here. So the greater change in energy will have a light come out that has higher frequency, and therefore, if you look at the electromagnetic spectrum, will fall further towards the ultraviolet. Whereas if we have a change in energy that is smaller, that corresponds to less frequency or longer wavelength of light, and would fall towards more of like the infrared. Or so if this one is violet, this one could be more bluish, maybe more yellow, somewhere that is further towards the infrared end. Okay, so it's important to realize that electrons absorb energy, come up, but then they also emit energy, and when they emit energy, it comes out in the form of light. Okay, on the back side of the review, there's this graph that a table that may get some of you stumped. So, today in class I asked about different sublevels. So, different sublevels are S, P, D, and F. The shape of the first sublevel is a sphere. So for each energy level, for n equals 1, n equals 2, n equals 3, they each begin with a shape or with a sublevel of S. It's the lowest energy sublevel, so electrons go there first, as according to the Aufbau principle. Electrons want to go where it's most energetically favorable for them. They want to go where they can see the most nucleus, and they want to go, and that means the least amount of energy they have to exert. So, but there's only one of these orbitals in each energy level. So how many can they hold? Well, each orbital holds 2 electrons. There's only one orbital, so only 2 electrons. Okay, in the p orbital, in the p sublevel rather, it has 3 orbitals, and they kind of have this dumbbell shape. Somebody laughed at me today for calling it a dumbbell shape, but I feel like, I don't know, kind of look like dumbbells. And this last one will come kind of out of the screen. Good, so they have this dumbbell shape. Now for the number of electrons it can hold when full, so it has 3 orbitals. Each orbital can hold 2 electrons. So we've got 2, 4, 6, so 6 electrons can be held. The d orbitals kind of look weird. They have kind of ballish shapes that kind of fill in between. We don't need to know the exact shape of those, but we need to know that there are 5 orbitals. Total, and if there are 5 orbitals, each orbital contains 2 electrons in this area. So 2 orbitals in each of the 5 orbitals, 2 electrons in each of the 5 orbitals means 10 electrons. Okay, F has some really weird ones. I can't even remember how to draw those. So, but it has 7 orbitals. So if there's 7 orbitals, 2 electrons in each orbital, end up with 14 electrons total. Okay, so for orbital diagrams, this is kind of what we're getting into that I feel like maybe a few people may be struggling. So let's look at a couple of these really quickly. So for beryllium, it has 4 electrons. And so if you think about this, this would be 1s, this would be 2s, these ones together would be 2p, and so on and so forth. So if beryllium has 4 electrons, that means 2 can fit in the 1s, 2 can fit in the 2s, and that's it. That's all we need to do there. So there's still a lot of left open orbitals that we didn't even need to use. Okay, so let's go to vanadium. It's a little harder. 23 electrons. You can look at the periodic table to prove that to yourself. So let's count them. 23. So 1s, up and down, up spin and down spin, according to the Pauli exclusion principle. Whoops. Up spin and down spin on the 2s. This one fills all up first and then fills down. Okay, so let's count and see where we're at. 2, 4, 10. So we still need 13 more for vanadium. So we're going to go to 3s, have an up and a down. 3p for this area. So we have up and down, up and down, up and down. I should have filled those all up arrows first and then down arrows. So what are we at now? So we have 10 to here, and then we have another 12, 14, 16, 18. We aren't trying to 23. Okay, so we need up and down. So this is a 4s2. So now we're at 20. Now all we have for the 3D is going to be 1, 2, 3. Good, so let's count them one more time to make sure we have 23. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 1, 2, 3. Good. So I'll quickly erase those. Or maybe not. We can just add on top of them. So for bromine, bromine has a total of 35. So vanadium, we know we put in 23 already here. So let's just add on top of those. So we're at 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 30, 34, 34, 35. Whoa, had a glitch there. Okay, so 35 for bromine, so that is now bromine's orbital diagram. Okay, so for electron configuration, we want to do two separate ones, selenium and nickel. So for selenium we have 34 electrons, and for nickel we have 28. Alright, so let's just start out with selenium here. And for nickel we want to do the abbreviated diagram. So let me turn to periodic table here and make sure I get the right abbreviation. So selenium has 34, so let's go ahead and start those out. So we have 1s2 is where they're going to start out in. Then it goes to 2s2, 2p6, 3s2, 3p6, then 3d10 is skipped because it is higher in energy than 4s2, so the electrons, they go into the 4s2 first. We can see that just by following the periodic table around as well. 4s2, then we get to the 3d10. And if we count up to see where we're at, we have 2, 4, 6, 2, 4, 10, 12, 18, 20, 30. We need to get 34, so that leaves us with a 4p4. Get that there. There you go. 4p4. So there's your electron configuration for selenium. Okay, and for nickel, we just want to do the abbreviated one. It has 28 electrons. That puts it in D block. So we go back to the 3p orbital, and where the noble gas is argon, is the last noble gas before nickel. So we'll start from there. And so it goes to 4s2, and then 3d. Let's count them. Go over 1, 2, 3, 4, 5, 6, 7, 8. 3d8. So yeah, electron configurations aren't too bad as long as you follow the periodic table and know that the D block scoots down. So if we were to kind of draw a makeshift periodic table here, okay, then this is S block, along with helium over here, kind of fits over into that. This is P block, and this will be the D block. If we know the D block starts, or D block, maybe we can say D block is drop down. Because if we made a parallel line across, this is the 4 level, but we have to know that the D block is dropped down, so this starts at 3D here. And then it keeps going in that same way. So it's all dropped down. So this one is 5, but this one is 4. This one is 6, but this one is 5. This one is 7, but this one is 6. So maybe if you just remember it like that, so the D block is dropped down 1. So when you're filling these, when you're filling the orbitals and drawing up your electron configuration, make sure that you say 4s2, 3d10, 4p6, and then when you come back around, you can say 5s2 4d10. Just drop it down. So if we get that, then we should be good. Okay, good luck. If you have any more suggestions, put your comments in on the homepage of the website, and I'll try to get to them.